for this talk today. It's really a pleasure for me to give this seminar, and I hope it will be of interest to you. So I will just share my screen and hope it is fine. So the idea today was to give you a snapshot on what we did on non-lithium based battery technologies, with a special focus, as Kristina mentioned, on calcium. And it's nice that she finished by showing this figure from the Batteries Europe roadmap, because I think it gives already the view that there are many different technologies alternative to lithium, and that they have very different levels of development, and the timing for their development, if it takes place, may be very different. So essentially, as an introduction, I would say that with a temporal perspective, of course, we all know about the past of batteries and the breakthrough of Volta when building the first battery, just aiming at showing that the electricity did not have an animal origin. And of course, this was a breakthrough because one could generate electric current upon demand, despite the performance was not very good if we look at it with today's standards. But anyway, this was a breakthrough. This was published in the Philosophical Transactions of the Royal Society of London. Volta was given awards, was received by Napoleon, so pretty European already at that time. The next breakthrough was the development of rechargeable technologies with the lead acid technologies in France. Others came, like nickel cadmium by Jungner in Sweden. And I guess all of us would agree that the present battery technology is by all means lithium-ion. This was commercialized in the early 90s. It has boosted together with portable electronics market, and this development of portable electronics would never have been possible without the lithium-ion battery technology. But then when we look at the future, and I think that even if you asked a bunch of battery researchers or the people working in battery technology, you may have very different answers as to what is the battery technology of the future. And the reason is that now the field of applications for batteries has expanded a lot. So it's not only for portable electronics, where the amount of energy is in the range of watt-hour, and the most important thing is energy density. It has expanded into kilowatt-hour electric transportation, and here energy density is relevant, but safety is also very relevant, and cost and durability. And if one is thinking on the grid and, for instance, renewable integration, then we can go to the megawatt-hour scale. And of course, here energy density may be less relevant for stationary storage, but of course, cost and durability are very important. And if we are thinking of a widespread deployment of all these applications and the use of batteries, one should think, of course, of sustainability and the use of non-critical materials. And this will likely also involve the development of new battery chemistries. And this was already seen back in 2016 by the World Economic Forum at Davos, where the next generation batteries made it #2 of the top 10 emerging technologies just after the Internet of Things. So when thinking at the abundant elements, one can have a look at this periodic table, which is really not very I would say rigorous, because the area is supposed to be proportional to the abundance, but this is not even true, not even at the logarithmic scale for those here. This would likely be a much more representative picture. So you see that here on this part of the periodic table, there are very nice electropositive abundant elements which would make nice battery anodes. And of course, with those other compounds here, one could make really sustainable technologies. So when looking at those metals here you see the abundance on the earth crust and the cost of the raw material, which may be the carbonate or similar. And you see that there are many interesting alternatives to lithium, sodium, magnesium, calcium, aluminum. All of them are abundant and lower cost. And here one can think of two families of concepts. So first, the family is the metal ion concept. This is truly analogous to the lithium ion concept. Here, the metal is just a charge carrier. In this case, we would be substituting lithium by sodium, magnesium, calcium, etc. And the issue here is that if the charge of these ions is higher, Coulombic interactions would be strong, both in the electrolyte and in the solid electrodes. And this will certainly have issues with respect to power. And here, I guess one could expect performances similar to those of lithium ion. Of course, the energy density will depend on which are the specific electrodes materials that are being used, knowing that the voltage limit for the operation of the negative electrode is the plating the potential for plating of this metal. And I think one paradigmatic case of the metal ion technology is sodium ion, and I will just mention it a little bit, because I think it's a technology that has gone very fast to production, and the TRL level has grown a lot due to the analogies between lithium and sodium and the accumulated know-how in the field of lithium ion. And of course, another concept would be to make batteries using a metal anode. And in this case, as you know, for lithium, there is an issue with dendritic growth, and there are a lot of efforts to try to solve this. But one could think of other alternatives. Here you have different metals, and you have the gravimetric capacity in green and the volumetric capacity in gray. Of course, nothing compares to lithium metal gravimetrically, but it's not very dense. And in any case, in lithium ion, one uses graphite. So you see that one could have interesting figures of merit for all those metal anodes, especially for aluminum, considering that you would exchange 3 electrons per each ion. And the energy density is the product of the voltage and the capacity. So let's have a look at the standard redox potential. And for aluminum is intermediate, magnesium is somewhat lower, but calcium has a very low value very close to lithium. So in principle, one could expect a very high energy density for calcium negative electrodes, and then one would have to look for very good positive electrodes to match those capacities. So with respect to the sodium ion technology, which will be my first example, as you know, this technology is by no means new, and in the early days of intercalation studies, both intercalation of lithium or sodium or other metals were studying at the same time, but there were prototypes of full cells, full sodium ion cells using sodium cobalt oxide as the positive electrode and sodium lead alloy as the negative electrode. Cyclability was not very good at the time, but still. And of course, all of this was stopped when the lithium ion technology was commercialized by this time. But then the topic was somehow rediscovered later on. And here you see it's from a review back in 2014, all the compounds which had been shown to be useful as positive or negative electrodes for sodium ion batteries, and an estimation of the energy density of full cells using those materials as positive electrodes and hard carbon as the negative one, and comparison with graphite, LiMn2O4 lithium ion. And you see that in some cases one will have competitive figures of merit. And the same is the complementary graph, thinking of different negative electrode materials versus a layered oxide as positive, and again, comparison with lithium ion. So as I was mentioning, this concept has witnessed a fast progress due to the similar chemistry with lithium. But of course, there are also significant differences which need to be taken into account. So in ionic radius, which will induce difference in coordination preferences and crystal chemistry. So not all the electrode materials which work for lithium will have a sodium analog, which will work as well. Also, the polarizing character, which is due to the higher radius of sodium, is different. So this will affect both diffusion and kinetics. Solvation energy will also be different, and then the solubilities of sodium compounds will be typically higher than for lithium compounds, and this will impact the stability of the SEI. Alloying behavior is different, and that's why sodium does not form alloys with copper electrochemically, and aluminum current collector can be used in both electrodes in sodium-ion technology, which is an advantage. And another significant difference is that graphite does not intercalate sodium, or at least unsolvated sodium, and typically hard carbon is used instead. And I would like to redirect you to this paper where there is really a nice cost and resource analysis for sodium-ion technologies, and figures, numbers are put into these ideas, and this will give you really an idea of how the technology has been progressing. And also, I would like to mention some of the European startups that are working in this topic at the moment. First of all, Faradion, which was the first one created, and they have an interesting roadmap, and they are now doing cells which are similar in performance to graphite LFP lithium-ion. They use layered cathode materials and hard carbon. They do these pouch cells, and this paper is very interesting, where they describe all the roadmap since they started to produce cells, and how they were improving performance and by improving the different battery components. Later on, Tiamat was created in the north of France. They are producing cylindrical cells, and in this case, the positive electrode is a polyanionic one, but I think they are still doing also very well, especially in terms of power. And other companies, for instance, are Altris in Sweden, who is looking at Prussian blue analogs or Prussian white as positive electrode materials for sodium ion, or even this other company in Wales, which has also recently built a pouch cell line. So as you see, there is a lot of activity in Europe on this technology, and the TRL is quite high and has increased a lot in very short time. And now I will move to the main part of the talk, which deals with calcium metal batteries, which is just the opposite extreme. We were not the first to think about the calcium being an interesting electrode for batteries, because it was somehow obvious that it is electropositive and abundant and so on. And the first report of attempting to use calcium to the best of our knowledge was done in the 60s as an anode for thermal batteries for military applications. There were also some attempts to use it with solid electrolytes, but no major studies of the redox mechanism or so were done at this moment, just prototypes being assembled and some performance measured, but they did not develop beyond that. Then in the 90s, there were studies by the group of Emmanuel Pellet and Israel and Stankiewicz in the US, aiming at substituting lithium anodes in the lithium thionyl chloride technology by calcium as a safer alternative. So calcium would have a higher melting point and also a higher conductivity. And the main issue would be that upon cell reversal, there will be no calcium plating. So it would be safer, and the reason why no calcium plating takes place was thought to be that the SEI in this technology is consisting of calcium chloride, and then this does not enable transport of calcium ions. So then I would like to show you some back of the envelope calculations. I told you that a priori calcium looks as an interesting anode, but could we pair this with an interesting cathode? Are the numbers feasible? So we took this Excel spreadsheet from this paper by Eric Berg and co-workers, where they estimate parameters for performance of a single cell, consisting of either two porous electrode or one porous electrode and one metal, and they take realistic values from the lithium-ion technology with respect to porosity, density of the electrolyte, and so on. So we took this, And we just simulated cells using current collectors of aluminum on both sides, using a porous cathode and then a calcium metal anode. And this is what we got. This is the volumetric energy density or the gravimetric energy density considering calcium and hypothetical positive electrode materials with operating voltages between 2 or 4.5 and capacities between 50 and 300. And you see that for cathodes with moderate, I would say, figures of merit, we could be already on par with the lithium-ion battery technology. So the prospects of good performance are real. But unfortunately, the reports in the literature were not that promising. And after the papers I mentioned to you, there was a seminal work by the group of Doron Auerbach, who attempted again calcium deposition in organic solvents, pretty much like those used for the lithium-ion technology. And they concluded that it was not possible. And again, the reason seemed to be that the SEI did not enable transport of calcium ion. And of course, then if there is not suitable electrolytes for plating, this hindered a lot the development of cathodes, despite intercalation of calcium in some compounds was tested, but it was really scattered studies. And as this DARPA adage in the US said in the 60s, technology is always limited by the materials available. So I like to use this graph, which is imported by from Patrick Johansson, who likes to show these ideas about why we do something. And in this case, well, we were interested by the potential performance of these calcium batteries, because this technology could be sustainable, especially if for the cathode we would use abundant metals, but also we were sparked by scientific curiosity. So the first question was to know why is the electrodeposition of calcium not feasible? Is it because the migration of solvated calcium ions in the electrolyte is hindered, or it is desolvation of calcium ions at the surface of the SEI, or transport through the SEI, as was thought before, or even nucleation? And we realized that the issue was really formation of ion pairs within the electrolyte, and that just by simply increasing a little bit the temperature using some specific electrolyte formulations, we were able to achieve placing and stripping. Here, the electrolyte is 0.45 molar calcium BF4 in ECPC, and you see the cyclic voltammograms at 100 degrees C. This is the calcium deposits. And of course, this is far from ideal because the efficiency is not very good. There is quite a lot of electrolyte decomposition, but still we were able to see by X-ray diffraction that this is calcium metal. And here you see a symmetric calcium-calcium cell. You see that they are huge, the polarization is huge. This is 100 degrees C. And just to benchmark, this is lithium-lithium symmetric cells at room temperature. So really still a lot to improve, but at least we showed that deposition of calcium was possible despite all the issues. Later, other studies were done with other alternative electrolyte formulations. So that the group of Peter Bruce reported this formulation with much higher efficiency despite lower stability upon oxidation. And in this case, there is also formation of a sort of native SEI between the deposited calcium and the electrolyte, and it consists of calcium hydride. And then later on, there were also reports by the group of Linda Nazar and the group of Zirong Saukarger and Max Fichtner in Germany, with other salts also containing boron. And there is also work going on by the group of Robert Dominko in Slovenia, in all cases trying to look at new electrolyte formulations for the best efficiency in calcium plating and stripping. So for the moment, nobody's perfect, but at least we start to have a bunch of formulations to work with. So at that point, we started to look for cathodes, and we used the electrolyte with which we had been working, because calcium BF4 is commercial, and also because of the stability at high voltage. And here we were facing a lot of issues with the experimental protocols, because one cannot mimic what is typically done within the lithium-ion battery technology, because ideally one would like to assemble half cells with a calcium anode, but I show you that calcium anodes were very polarized, so really to know what's going on, one has to use 3 electrode cells, and then the question is which is the best reference electrode to use, and we had to calibrate and so on. So this took us a while, but finally we developed a set of protocols which were reliable to test potential positive electrode materials. And we were exploring a little bit the periodic table. We were focusing on intercalation compounds with transition metals as redox center, either having or not calcium in the crystal structure, because of course, if we have a calcium metal anode, there will be excess of calcium in the cell. And also we were exploring oxides, sulfides, nitrides, etc. And amongst these, we explored traditional intercalation hosts like V2O5 for TiS2, but also, I would say, new hosts or potentially new hosts, which were calcium transition metal anodes, transition metal oxides, sorry. So one of the compounds which we thought was interesting was perovskites, because this is a very rich family of calcium metal oxides, and amongst them molybdenum compounds seem to be very interesting, and we were able to prepare it, but there was no way to electrochemically extract calcium from the crystal structure, which we understood with the help from Elena Arroyo at Universidad Complutense de Madrid, who did the DFT calculations and was able to realize that the migration barrier for calcium in this crystal structure is huge, is 2 electron volts. Same, we were also interested by calcium Mn2O4, and for this stoichiometry, there were calculations by the group of Kristin Persson in the US. She considered the spinel polymorph, which is not known because calcium is not that stable in tetrahedral position. But if it was possible to prepare this compound, apparently the migration barriers for calcium would be very low, especially because calcium, as I was mentioning, is not that stable in this, would not that be stable in this coordination. So instead, we looked at the stable polymorph, which is the Marokite one, which has these double rutile chains and these tunnels along the crystal structure, which looked very interesting. But again, when we prepared it and we tried to extract calcium from it, it was not possible. We saw a huge oxidation, which resulted to be only electrolyte oxidation. The E3 diffraction pattern of this compound did not change. And the calculation of the migration barriers yielded also a very high voltage. So this time we decided to revisit TiS2, and there was precedent of intercalation of calcium in TiS2 by Jean Rouxel in the 70s in Nantes, in France. And they did this with using calcium dissolved in liquid ammonia, and they were able to intercalate calcium in between the layers of TiS2, still coordinated by ammonia, and then by gently heating, they were eliminating ammonia. So this is what we got when we tested it electrochemically. There seems to be a reversible behavior, but the polarization is huge, so really not really a practical interest. So when we did the diffraction ex situ at different points, this is what we see. There is always a significant amount of TiS2 which has not reacted, so there is likely an issue with kinetics despite 100 degrees C. But we see the formation of different phases, as you can deduce from those peaks at low angles in diffraction. And we were able to identify some of them. So for the first one, the one with the highest interlayer space, we believe that this phase has a solvent co-intercalated, so it's solvated calcium that intercalates. Then phase number 2 would be the same phase with naked calcium that Jean Rouxel had prepared in liquid ammonia, and then about phase 3, it could be maybe a stage 2 phase. And as you can imagine, with these patterns, it was not possible to refine the calcium occupation and in these crystal structures. So we turned to complementary characterization techniques to make sure that really these structural changes were related to intercalation of calcium, and we were able to do transmission X-ray microscopy at the calcium LH, at the ALVA synchrotron. We were using different compounds as standards, and here is an image of what we get. This orange shell has a similar calcium density as calcium carboxylate, so it's likely produced by electrolyte decomposition. In red, this would correspond to calcium fluoride, which we also see on diffraction, also due to electrolyte decomposition. But then these pink bubbles would indeed correspond to calcium inside the TiS2 particles. Of course, polarization is huge, and as I was telling you, calcium anodes are not the best. So at this moment, we were thinking of separating issues and just not importing problems of calcium anodes when looking for cathodes, and trying to decrease the temperature, because testing at 100 degrees is also a guarantee of electrolyte decomposition. So we were looking at other counterelectrodes, and the first obvious choice is activated carbon, and this is what we did. The main issue here is that the balancing of the cell needs to be carefully addressed, because the capacity of activated carbon is very small due to the capacitive mechanism, but still, if this is taken care of, one can have successful results. And this is what we did. In this case, we use calcium TFSI, which is also commercial and much easier to dry than calcium BF4. And we saw that at 100 degrees C, we have the formation of the same phase as we saw, not phase 2. Surprisingly, even at 60 degrees, and we can also see the formation of this phase even at room temperature, which was quite interesting. Then we were following this intercalation mechanism by operando diffraction, and this was done at ALVA. This is a cell, an operando cell, which enables circulation of a fluid to increase temperature. And this is what we got at 65 degrees C, and we are still investigating this, because the redox mechanism seems to be much more complex than what we have thought. And in fact, the position of those peaks seems to be evolving in the course of cycling. So the mechanism is something that we still need to understand better. So then when looking at the other group of compounds, so calcium transition metal anodes, transition metal oxides, sorry, we were interested in this compound, which is a derivative of the hexagonal perovskite, and its crystal structure is made of columns of alternating cobalt, octahedra, and prismatic coordination, which are sharing phases, or in some cases one can have also manganese, and there is calcium between these columns. And our idea was that maybe this crystal structure would favor calcium mobility through these columns. We prepared this compound. It is really easy to prepare. This family of compounds has been studied a lot for its magnetic properties, with the intra and inter couplings between the chains and so on. And we were able again to do operando diffraction at the ALVA synchrotron using these coin cells at room temperature. And this is somehow the electrochemical curves that we get. So we get the oxidation, and then we get the reduction, and then we were able to further reduce again XC2 the cell and take some patterns at the end. And the result is the same for the cobalt and for the cobalt manganese compound. This is what we get. So upon oxidation in red, what we get is that the pristine phase amount starts to decrease, and a new phase, a new oxidized phase appears. But then upon reduction, as you see, there is nothing going on, and I don't have the blue pattern here, but it's exactly the same one as the greens. So the thing is that we were able to elucidate the crystal structure of the oxidized phase, and we were able to refine the amount of the occupation of calcium. And it's clear that we have electrochemically extracted calcium from the crystal structure, but somehow this does not seem to be reversible. So this can be to intrinsic structural constraints. Maybe the migration of those calcium ions in this oxidized crystal structure is more hindered than in the pristine one, or it may be due to the fact that to reintercalate calcium, you need to desolvate the ions from the electrolyte, and maybe the desolvation energy has a role to play here. So this is something that we're still trying to address. And finally, I would like to mention other two cases which we investigated again in collaboration with Elena Arroyo in Madrid, who did some screening of different calcium transition metal oxides to look at possible migration paths for calcium in the crystal structure. And when she found low energy barriers, she came to us to pursue the experimental study. So the first interesting compound is calcium-2 MnO3.5. This is a derivative of the Rudesland-Popper phase calcium-2 MnO4, which has some oxygen vacancies, which, as you see, one can see very clearly on the AB plane. And in this case, the coordination of manganese is not octahedral because there are those oxygen missing is pyramids. So she calculated the migration barriers along different pathways, and you see that in this AB plane where the vacancies are, the migration barriers are, I would say, tolerable, about 1 electron volt. And of course, when one considers a migration along the C direction and these perovskite slabs, then it is the barriers are very high. But still, this was considered interesting for experimental investigation. And another compound with which she came was calcium V2O4, which is has a very similar crystal structure than the manganese phase that we had been studying before. And in this case, she found that the migration along the tunnels has very low barriers, about 0.5 electron volts. And if we were able to extract almost all calcium from the crystal structure, then the barrier would be a little bit higher, but still those were considered interesting for electrochemical investigation. And also in parallel works by the group of Piero Canepa in Singapore came with similar values. So we prepared those compounds and we oxidized them electrochemically. And the first thing is that the oxidation, the potential at which they oxidize is huge, is equivalent to 5 volts versus calcium metal. So we will for sure have a lot of electrolyte decomposition here. But when we did diffraction of those materials, we saw that there were changes in the diffraction pattern. So really there is something going on in the material. So this is the pristine calcium vanadium oxide, and this is the oxidized phase, and the same for manganese. So again, this is operando diffraction, in this case for the manganese compound. And what we see is similar to what we saw with the cobalt compound. So we see some evolution of the diffraction pattern upon oxidation. Here you see this process. And then after oxidation, when we reverse the sense of the current, despite we get some electrochemical response, there are no changes in the diffraction pattern. So this evolution seems to be irreversible. The issue is that when we were trying to refine the occupation of calcium in this oxidized phase, we ended up with the same calcium amount of the pristine phase, which means that the charge compensation mechanism must be different. So if it's not extraction of calcium, it could be intercalation of anions. And in fact, when we did the Fourier map, we were able to see some electronic density in this position, which was the oxygen vacancies, which we saw before, and also on this plane in which the Rudesland-Popper compounds are known to intercalate fluorine. So we did some attempts to confirm whether there was fluorine intercalation. It could have been oxygen maybe as well. We confirmed the presence of fluorine by yields and EDX, and we were able to even estimate the amount, which would be about 0.6, which would be in agreement with not only this position being filled, but also a small amount of fluorine there. And the definite proof that this was fluorine due to electrolyte decomposition was that we performed different electrochemical oxidations in other electrolytes containing or not fluorine. And for instance, when we use LiBoP, which does not contain any fluorine, we don't see any changes in the diffraction pattern. But when we use LiPF6, which contains fluorine, or even cesium fluoride, we do see this oxidation. So indeed, what happens here is that when we oxidize the compounds, we get intercalation of fluorine. So this will not be useful as a positive electrode for calcium batteries. And finally, the last compound. Again, this is calcium V2O4. This is operando diffraction data at ALBA. We see again evolution upon oxidation, but in this case, upon reduction, we do also see an evolution of the X-ray diffraction pattern, despite the pathway seems to be different. And this is something which we are still investigating. So we seem to have a two-phase process here, and here we seem to have the formation of a solid solution. And this oxidized phase was found to have a stoichiometry of calcium 0.7204. So it's really not that much that we have been able to extract it, and we're already at a very high voltage versus calcium. This is just the phase fraction of the pristine and oxidized phase, which of course one decreases and the other increases upon oxidation, and upon reduction you see that the amount of each phase becomes stays more or less constant, despite we increase the amount of calcium in this oxidized phase in agreement with the formation of a solid solution. So we did some attempts to build cells which would attempt to cycle in different conditions. The profile does change upon cycling, and of course, again, there is a lot of electrolyte oxidation, so it's something that we are looking at it more closely, and there is still room for improvement, but at least this is the first time that we have shown that calcium can be extracted and reintercalated in the crystal structure of an oxide compound. So to sum up a little bit, we were studying positive electrode materials, and we saw all types of behaviors, reversible intercalation of calcium, but together with solvent molecule for TIS2, some irreversible behavior, some electrochemical oxidation, in some cases involving indeed extraction of calcium, in others involving intercalation of fluorine, but irreversible, but also for the case of the vanadium compound, the behavior seems to be reversible. So at this point, I think that the role of the calcium interaction with solvent is crucial, and there is the need for more electrolyte research for sure. And another take-home message which I wanted to give was the need of use complementary characterization techniques when looking at multivalent battery chemistry. So one does have to do blank experiments. This is just aging in the electrolyte. So this particular compound was reacting with the electrolyte. This one has to know the need of 3 electrode cells, the need of complementary characterization techniques, because there is no real standard. There is no standard electrolyte. The anode also has issues. There can be many side reactions going on, as you saw, for instance, here with fluoride intercalation. So one has to be very careful when interpreting results. So nothing can be taken for granted. You need to make sure that your electrochemical setup is reliable, and there are many issues that one should look at. And also for the positive electrode materials, care has to be exercised when interpreting just an electrochemical response. And this is a table of all the compounds for which calcium intercalation was reported, so already 2 years ago. And in some cases, you see that there is only the electrochemical response, so then one has to have a critical view, because some of these interpretations may be biased because all of these phenomena and side reactions that can take place. So overall, the message is that the development of new battery chemistries can be very slow, especially if there are not preliminary technologies or knowledge which one can import, and this is the case for calcium. This is a graph which was usually being given by Ralph Broad with different steps in the development of a new technology, and in each step you need more staff and a higher amount of material and so on, but finally it would take between 10 and 20 years to reach the market, if successful, because for some concepts you may not just be able to go from one step to the next one, because the performances would not be as good as expected. So just to finish with a quotation by Walt Disney, because of course all this matter is complex, but I have always been an optimistic person. And just I want to acknowledge all the people that contributed to this work. So the ICMAB team, especially Alexandre Ponrouche, who did all the studies on the calcium plating. Ashley Black, who worked a lot on the cathodes, and of course, long-term collaborators like Elena Arroyo or Patrick Johansson, and the ALBA team, Patrick Rosiat-Silimat, and Fanny Balde at Toyota, who gave us the possibility to start with this topic, because the initial project was funded by Toyota, and then we had funding from the European Commission. And so this is all on my side, and if you have questions, I will be happy to take them, and thank you very much for listening.